So, hello everyone. This presentation will be actually joint between my colleague Philip, who is actually the creator of the navigation system that I will present, and me. Then we do this shared presentation because it's a bit ahead of time and we don't have it actually prepared fully. So I will try to use my experience to skip those gaps that are remaining in the slides. So let me first slightly introduce my recent work. I've been to the UK for the last 5 years, and in UK I was working on robots that are supposed to reliably operate for really, really long periods of time. So actually one of these systems was used in a robot that's operating in Vienna in a hospital, and in there the robot achieved autonomous no-hands operation for 4 months. The robot is actually acting as a guide and as an infoterminal in the hospital, and it's learning the habits of the people there, and it's basically trying to adjust its activities and spatial temporal models that you will see in the other presentation later on. Another example of my work is a very recent contest we have been to. This contest happened in Abu Dhabi. It's the Mohammed bin Zayed Robotics Challenge. And in there we have been quite successful actually, because we went only for 2 contests, but we won 3 medals by chance. So we won actually gold, bronze, and silver, and this lump sum of money, which unfortunately was not sent to our bank accounts, but to the school bank accounts. So it's not likely that I will see any penny from this, but that's how it works. In both of these systems, vision was actually used as the main means of the navigation of the robot. So in here, the robot used also a SIG laser for navigating around, but at some areas we actually had to use vision. And in this case, we had actually drones that had cameras that had to recognize objects on the ground and pick them up. So today I will talk about visual navigation. Actually, it's an extension of a system that was used in World War 2006 and 2007. And then the organizers actually prohibited to create maps. So we had to change the system, and it was too much of a hassle. So maybe we will invent something else for the next round. But this is a system that originally was created to robot. So if you have a look how normally visual navigation in robots works, then people are using something that's called SLAM. SLAM is called simultaneous localization mapping, where you use the camera that's on board of your robot to extract some image features from the camera image. You find correspondences between the sequence of these features. You will mesh them to the map, and then you calculate the robot pose, and then you actually calculate how the robot is supposed to move. So in theory, this is working perfectly fine, and in most laboratories, this is also working pretty fine. We also have data sets that have been very carefully tuned, and with fancy cameras, etc., where actually visual SLAM is working quite nicely, like the videos. However, if you deploy your robot outdoors, you typically find situations where you don't see enough features to perform any kind of matching. The environment tends to change its appearance, so you can't really establish the relation between what you see and what you saw before. And often there are problems with precision and complexity of these algorithms. And especially with the precision, it means that you need good calibrated cameras, and you need equipment that's basically, let's say, a bit more expensive. That's not available to us. And even if you calculate all of this stuff, it might be too late for the robot to actually make a decision about its turn. So to overcome these issues, people have typically employed probabilistic approaches. And when they checked what's the actual interplay between the robot position and the robot heading, or the robot that's actually going on the ground, they found out that it's the heading that's the most important variable in robot navigation. So in our case, we are actually saying that heading estimation is actually everything. You don't have to estimate the robot position, the XY position at all. You don't have to perform localization when you want to navigate the robot around. And if you only ensure that the heading that the robot is using its exteroceptive centers, like cameras, to correct only its heading, then you can actually prove that the robot position error remains bound. And this allowed us to create a very, very simple visual navigation system that was successful in RoboTour, and that was also used in many of these systems that I've been showing, and you can rather assume that it was working pretty well because we have been quite successful with that. So that's the theory, that's the introduction of the system, and I will let my colleague Philip to actually describe how this was implemented.
Okay, so the system that we created consists of two parts. The first part is the mapping part, where the human operator drives the robot through the environment using the teleoperated drive. And from this teleoperated drive, he creates a map. And the second part is the navigation, where it uses those maps to navigate itself through the environment. And I will show you on an example how the system works. So we create a path using the teleoperated drive, and we remember the odometry and the distance. And every distance, every certain distance, the robot remembers all the features from the map, and it creates a local map. So, like the path is divided between local maps, and that's for the mapping part. And for the navigation part, he remembers he knows his distance, and then takes the map that he created, the nearest map, and matches it with the image he currently sees, and matches the features together. So and then does this all the way, and uses these matches to convert to get the better heading, because the features and their vertical difference, he wants to get it to zero. So the robot, when he changes the heading, then the map tells him to get the difference to zero. So all the way through the drive, the robot corrects the heading based on the map that is currently he sees. So the next map allows all the maps together. So I will show you on the video how the algorithm works. So here, the blue color represents the current image he sees, and the green ones, the green is the features loaded from the map. He then matches those features and creates an histogram loading, and the histogram uses it to drive. So the histogram tells you to get the difference to zero. And it uses, you can see when the heading changes, the histogram moves to the side. And on the second,
so the point in here is that if you create a simple, a very straight map by the robot, like the blue one, and you let the robot to navigate around to actually repeat this step by the features, and you displace it, then what you will find out that as the robot navigates along it, because it's using the image features to steer, to determine its heading and to steer actually, then you will find out that it slowly converges to the original path. And what you will find out that all of these trajectories actually intersect at the point where the features are, which is logical because the robot basically drives towards those features. So it's in here, where was the window and the background, the robot saw something and the robot is actually going towards this point. So with this insight, we are able to create a simple model of the robot position error as it moves along the path. This will be a bit tricky, so I will try my best to explain. So imagine that we have taught the robot a path that's actually some curve, and that the robot actually thinks that it's on a certain spot on the map, and as it moves along, we can check what's the robot position error, which is the robot XY coordinates in this local coordinate system that's created at the point the robot moves along. And let's say that we actually check how the robot position error changes over time. So what we do is that first, imagine that the robot is stationary and only the reference point is moving. And what you will find, what you will actually do is that there will be some speed that the reference point is moving. That's the speed that the robot remembered that the point was moving with. So this is the speed. And also there was some rotation kind of component. So if the robot was stationary and only this reference point was moving, there will be some rotation that comes from the XY position of the robot and the actual speed of the robot. So this comes from the reference point moving. Then the robot also moves by itself, so it moves with some velocity forwards. And there is some noise that comes from the intersection of the robot sensors and from the odometry, etc. If you look at the Y component of the robot position, then again there is something that comes from the rotation. And the speed that the robot is moving in the Y component is actually given by its ability to drive towards the feature that it sees in the front. So the shorter, the closer the features are to the robot, the more shorter is this triangle, and the more faster the robot converges to the original trajectory. So again, there is some noise that we have to add because the sensors and the odometry, etc. So this is the motion model of the robot, right? If we actually rewrite it into vector matrix form, you get this thing, and this is a linear system, and you can actually say that the linear system is stable, which means that these values don't diverge if the eigenvalues or if the real part of the eigenvalues of this matrix are lower than 0. So if you calculate the eigenvalues of this matrix, you will arrive to this simple quadratic equation. And the solution of this equation, and you can see that either the expression under the square root is a negative number, which means that the real part of the eigenvalues is really negative because the speed and the distance of the landmarks is positive. Or, if it's real, it can be at most equal to the speed of the robot divided by the distance of the landmarks, so it can be actually equal to this. And the only case this is equal to 0 is when the robot turning speed is actually 0. So only if you are traversing a path that's straight, this matrix or this system is not stable, which means that only in that case the robot can be divergent. As long as your trajectory has any kind of curvature, the whole navigation system is stable, even if you don't perform any kind of explicit localization. So simply by steering the robot to the features along any kind of path, you can prove its stability. And actually this is a novel thing. This is what makes the difference of our new system to the original one that was used in Robotour. Because in Robotour we had this kind of proof only for polygonal trajectories, so we had to move the robot straight, then it had to turn, and then it had to move again. In this case, we can go any kind of trajectory that's not only a straight line. So if we go a sequence of straight lines with some curvatures in the end, the system is still stable. So we will show an actual experiment.
So here in the experiment we placed a localization system on the robot, and here we can see that the red line is the mapping phase where we did the deliberated drive, and the green is where we put the robot approximately 1.5 meters away from the path, and wanted to look whether the robot converges to the path we created for him. We can see that after like second or third, the robot is basically at his start of the path, but there are few things that happen. For example, this line is the robot never converges to this line because the start of the trajectory is not the same as the end. So the robot starts every drive starts with a difference between the path approximately for some distance. So at the start, you must like adapt to the change of the start and the end, and after a few traversals, the robot approximately drives through the desired path.
So I would like to stress that this robot actually didn't have any odometry. We only set an EVM on the PWM on the motors, and we measure the time of travel. So there is no odometric system. So we did not really rely on anything that would make our stuff easier.
Here we put a flashlight on our robot and wanted to show whether the robot can do a drive during the night where the only things that he sees are the ones that he illuminates. During these experiments, we've encountered some problems. For example, like with the camera, which was Lucka talking about, and he discovered that the features that the robot sees are equal to the ones that drives during the day, because he illuminates the map himself and can go through this environment during the night.
Okay, so the main thing in here is that if the robot is illuminating the scene for itself, you typically don't see much. So the typical image that you get from the robot looks, at least in our case, it looks something like this. So this is the scene during the day. This is the scene during the day, and you really have a lot of stuff that you can detect in the image. And this is the night scene where you typically see only a few stuff. And also the stuff changes the appearance because you illuminate it from closer. And this system that we implemented is actually very, very robust to this because it doesn't require that you see many features scattered along the scene. And it's also okay only if you see only a few features actually in front of the robot. So as far as I know, I haven't seen other people doing night experiments with strong illumination. Typically, people are trying to use either LiDAR or some expensive device in this case. In our case, it was working quite nicely. So the main thing, what we presented, is a very, very simple teach and repeat navigation method. You can actually get the navigation method at this address. It's really simple. You can just drive the robot along a trajectory, tell it to remember the trajectory, and then you can actually tell it to replay. It's all based in ROS, so it's very easy for everyone to use. But also the core itself was not originally ROS-based, so you can easily extract the most relevant code that actually does this. So, yeah, if there are any questions.
Yeah, I would have maybe a question regarding the 8 loop of the robot. Because the proof is that it's limited. So it's not necessary that it will convert to the original 8, right?
It should converge to the original trajectory. It actually depends on the noise that's present in the robot odometry, etc. But what Philip was also mentioning is that it's very hard when you drive a robot around that you end exactly at the spot where you started. Right? So actually every time the robot is traversing the path again, there is a certain error that's injected due to the fact that the map is not perfect. So in that case, the convergence is violated because it's physically impossible to create a false path, right?
Okay. So you think it should convert in like perfect world?
In a perfect world without any noise, yes, it would converge. But if there is any noise, it would actually oscillate around the top.
Maybe there was the question of the logo.
The logo is a remnant from my previous employer. It's the logo of the University of Lincoln, so sorry, that was left in the presentation. So we tested the surf features. We also tested their GPU variant. But on that small robot that you saw over there, it was like computationally limited. So we used AGAST, a detector, which is a variant of fast features. And we used the brief features, which is a very, very fast binary extractor. Again, since the algorithm is robust by itself, you don't need a perfect image feature. And actually, you don't need SIFT or SURF, because the invariances that these features provide, you don't need them. You don't need scale invariance, you don't need rotation invariance, you don't need perspective invariance, because the robot is almost at the spot where it saw features before. So actually, brief and fast are often perfect. And I think that even on a computational constrained device, you can perfectly use it.
I wanted to ask something in connection to this. Again, I have seen, I believe, could you slide back to slide 7, please? Or before. Yeah, something like that. Even here, I can see a lot of features which are matched, but the pictures were taken at different times. So I believe that the trees must have changed, and those features I do not consider good to be matched at all. I understand when it is a feature matching between two frames taken just a fraction of a second apart, but it might work well. But if you take days between that,
yes, I completely agree. Actually, in the beginning of this year, I published a paper that's on a system that actually learns the features. So I give him really features from really different seasons. So somewhere you have snow and no foliage on the trees. Somewhere you have trees with the foliage. And the system is gradually trying to learn point-based features that are robust to this kind of environment change. So the feature is called grief, because it's a generated brief. It's based on these binary comparisons, so again, it's super fast. However, I agree with you that using the point-based features in these scenarios is going to be obsolete. With the advent of deep learning, you should be able to actually find like higher-level objects like the trees and this kind of stuff, which you can also have in the OSM, and use these kind of objects rather than features for the navigation. But the point is, regardless of the feature is, you can just use it to estimate the heading of the road. Because even if you have an object detector, it typically doesn't provide you with a reliable distance estimate of the object, but tells you the heading. And what we are saying is, if you see a few objects in your scene, you don't have to perform triangulation of the road position, just what the heading.
Just one comment. Like, why wasn't this thought the first one, and why the last one when a lot of people are not here? I think it would be really useful for all the other people that have already left.
I would have to ask why people are leaving. It's the
that's only for those who can stand waiting here. So.
Yeah, well, I was told that later talks will be more theoretical and less related to the competition.
Yeah, well, I mean,
that was the way to sort the talks. I would put this one on the first place and the other ones at the end, but never mind. It's just this
theoretical.
like the pure theoretical paper. This one.
actually,
that was really a difficult way to say that I like it.
I know that you want to say this directly. I really appreciate your comment. Okay, anyway, I can put the slide online, but if you go here, there are videos, there are explanations, there is the link to the paper, and there is the code itself, so you can really just take it and download it and try, and if there is any problem with using it, you ask Philip. So
it's really cool.
Thank you. So, yeah, so that's it.